Okay. I have prepared a tutorial about the general field of research in which my group works. I have prepared a tutorial assuming the typical attendee would be a student that doesn't know anything and might be interested on this. So I apologize if people that don't fit this profile doesn't learn anything new. Yesterday I gave a talk. Today I'm going to give that talk again with more explanations and a few more slides. So I'll start by giving an overview of what is atomistic simulation of materials. I will talk a little bit about density functional theory, which is one of the possible methods to use if the conditions are right. I'll show one example in detail of how to use density functional theory to predict the behavior of a new material. I'll talk a bit about future derivations, and I'll summarize. So, as I said yesterday also, today in a bit more detail, we consider an atomistic simulation of a material if we describe the macroscopic properties of the material by resorting to the very strong hypothesis that is made of atoms, something that was guessed more than 2,000 years ago. So now you know that your material, whatever it is, and however odd it is made of atoms, and these atoms will interact among themselves. And you have to use the laws of physics to come with a mathematical expression for this interaction. And here you have a very broad spectrum of models to choose from. I always start with with the simplest model we can think of, which is that the atoms are billiard balls. So the billiard balls, very tiny billiard balls, will not attract each other, will not repel each other. We don't even need that to learn something about materials. What the billiard balls will do is we'll set them up in motion at the beginning, and they will keep on moving on constant speed until they find each other, or they find the walls of the container if they are there, like in an ideal gas. When they find each other, they will rebound. Okay? The thing is, if you can write the Newton equations for this movement. It's very simple. It's uniform movement of particles, and just you have to also compute how they rebound. We'll do it in the next transparency. But the thing is, if you have more than 3 or 4, it's going to take you a long time to solve this with pen and paper, so you are going to need computers. And this is one of the main ingredients in our research. Everything we do with many computers. In 1962, Alder and Wainwright did what is the first molecular dynamics simulation, and using this very simple model, they were able to see that a system of hard spheres has a phase transition. So what they did is, again, you have a number of spheres large enough to represent your liquid or your solid or your material, and you know in classical mechanics everything about them. You know their position and their speeds, and this is enough, because for every 2 particles you can compute when they will collide. And when, it's very easy, again, if you set up uniform speed equations, you get to the time of collision, if this is going to happen, and once they collide, they will rebound, and again, assuming conservation of energy and conservation of momentum, it's very clear, it's very definite what the particles will do. Now, you can set up this in the computer for 508 particles, 512, or whatever number you want to do. These days people do million. Still, some people are studying this problem. There are things to learn. And now they do the simulations with millions of balls. There is an important ingredient that will come back later, so I'm going to mention it for this simple system, which is that you are going to have to set up boundary conditions. In principle, you could do the simulation inside a box, and the balls could rebound against the walls. But it's more efficient to do it with periodic boundary conditions. So you have a box, the balls are moving, and when this or when this ball leaves this box, it will enter here. So this particle can collide with any other particle in the box or the images. There are images of the balls all around them. Okay? This is, in principle, an artifact that is useful in some cases, like when you study crystals, and we'll see it later. More than an artifact is something that describes your system exactly. In a crystal, you can assume that you have infinite periodicity. If you do many simulations, you choose different densities of the balls in the box. So in some cases, you have a lot of empty space. In some cases, the balls are very crowded. You can, for this very simple system, you can go to your statistical mechanics equations, and you can see that you can write the equation of the system equation in a very simple way that just depends on the radius of the ball, the number of particles, the average speed, and then the change in velocities every time there is a collision. You could deduce this formula, and with this, for any given volume, you can get the pressure of the system. You can do this for many volumes and for many different initial conditions, and what you see is that there are two phases. Okay? Depending on the initial conditions, you will end up in a state that looks like a solid, or you will end up in a state that looks like a liquid, and the balls can wander around and pass each other. And this was the main result of this model, of this simulation. So again, the point is, you can write this program in, depending on your ability with computers, in a few hours. And you can solve it, and you can learn something from it. And this is the main point of our work. These days, instead of hard spheres, we work mostly, I mean, again, I'll make the point later. It doesn't matter the method you use. You use the method you need to get the information you want from the system. If you could use hard spheres, you should use that, because it's faster to run. What I'm saying is that these days, most of the studies in computational materials are done assuming that the atoms are not balls, but they are nuclei with electrons, that the electrons fulfill the Schrödinger's equation, and, or our approximation to it, since we cannot solve the exact one, and using a lot of computer time, we can know what the electrons do, and then with these properties, we can know if the material is hard or is soft, is transparent or not, is a conductor or is an ice insulator. And we can compute many of the properties of it. To give an idea of the range of materials that this kind of method covers these days, this is a world map made by going to what is the main advertising list for this kind of community. So everybody puts ads for looking for students or advertising conferences. If the word is in big letters, that word is a lot in those ads. If it is in small letters, well, all the ones that are here are a lot. There were many more words that didn't make it to the map. So you can see that there are, for example, a lot of kinds of materials that are studied. In our case, we study a lot of oxides, we study crystals, but there are a lot of applications to interfaces, optics, all kind of thing. And here in big there is experimental, because many of these works are motivated by experiments or are done in collaboration with experiments. The largest word here is DFT. DFT stands for density functional theory, which is one of the methods we use. Again, I want to make the point again that the method to use, and in our group we have used several of these. We try to use the method that fits better the problem we want to solve. Or maybe we can use more than one method, getting information from the most accurate ones to use methods that are less accurate but faster and can be adapted to this one. So basically, these are circles that show how many papers were published recently using these methods. As you move from left, from my right to my left, the methods are more accurate, meaning that they will give you results that are closer to experiment with less and less macroscopic input. But this has a cost, because the more you go to this side, the more time your calculations take. And there is a point in which it takes so much time you cannot do them. So depending on what you want to study, if it is a molecule of water, maybe these methods are already, maybe you can use them, maybe it's too long already. So on the part of methods that are very well suited for very large systems, you have things like, the simplest thing you can use is a pair potential. So it's the next step to the hard spheres that we saw. You just have atoms that are balls, and the balls interact with some mathematical, they interact, they exert forces on each other that you can represent by some mathematical expression. And they do this in pairs. So they do it in pairs. So you sum for all pairs in the system. You can use force fields in which you not only do pairs by atoms, but the interaction will depend, for example, in the angles between the atoms too. So there will be 3-body interactions, 4-body interactions. Other models take into account, like these shell models, take into account that there are electrons in the, for example, the ones I'm aware of. There are electrons in the atoms, so under an electric field, there will be a cloud of electrons that can be a sphere that will move one way, and the nuclei will move another way. These methods, for example, with either this or this, I don't remember, there has been, I saw a publication in which they do molecular dynamics of a virus that has 1,000 atoms. So they build the virus atom by atom, and, sorry, not 1,000, 1,000,000. So atom by atom until you have 1,000,000 atoms, and then you evolve it and you see what it does for a few picoseconds, or even up to a nanosecond. And then you learn which part of the virus are stable, etc., etc. The next step is to acknowledge that there are electrons that behave with a quantum nature. So there are electrons, and they are quantum electrons. It's not just a sphere of charge that moves in an electric field. And there are methods, but part of this, these interactions between electrons and atoms are described by some semi-empirical data that you get by fitting to either first principles, either more exact methods, or by fitting to experiment. And these are methods like tight binding and the embedded atom model. As I said, the most used method, because it represents a very good compromise between accuracy and how complicated your system can be, is density functional theory. And I'll say a bit of it in the next transparencies. If you need, but these methods have a very important approximation. Are defined by a very important approximation, which is that each electron sees an average of the rest of the electrons in the system. For some materials, this is a good approximation. For some materials, this is a bad approximation, and you have to go to this side, in which each electron is treated independently, and if there are correlations between electrons, this correlation can be obtained. So just, I almost don't have equations, I think, in this presentation, but I have a few, just to give an initial idea of what density functional theory is. This is the Hamiltonian that goes into the simplest Schrödinger equation. There is a term that is the kinetic energy of the electrons. I'm going to assume only that the electrons behave according to quantum mechanics. This is in the Born-Oppenheimer approximation. It doesn't really matter. It's the simplest thing we can do if we want to treat electrons independently. Not independently, but as a quantum particles. So there is a kinetic energy. There is a interaction potential between them, which is just the electrostatic interaction between negative charges. And usually this system of electrons is in the fields an external potential that in a solid, in a material, is the potential created by the nuclei. So this is your Hamiltonian. If there was no interaction between electrons, then the solutions would be you could get them for independent electrons. Each electron would feel the external potential and do something about it, but there are no other electrons, so this is solvable. You can solve that in the Schrödinger equation, but that is not the case. The electrons also feel each other. So usually you have your system, so this and this are always the same. This is the kinetic energy, so it's just the second derivative of the wave function. This is the interaction potential, so it's just the 1 over r times the electron charge. So once you and if you have a material, you know where the ions are, and those are the ones that exert an external potential. From the external potential, you could solve the Schrödinger equation and get the wave functions. From the wave functions, you can get the one of them that corresponds to the ground state, the lowest energy. And from that, if you want, you can get the electron density. And this is was well known immediately after the publication of Schrödinger's mechanics. What is new and what defines density functional theory is that it is possible to go in this direction also. So in like 40 years later, after quantum mechanics appeared, almost 40 years, Hohenberg and Kohn proved that if you have the density, you can get the external potential. This is not intuitive, although it's not also impossible to believe, because the density gives you, for example, the position of the if you know the density of the electrons in your material, you know where the ions are, because the electron density picks at the ions. With the curvature, you can know the charge. So this was what started density functional theory, to prove, and the proof is not very complicated, that given the electron density, you can get the external potential, so you can get the Hamiltonian, so you can get the energy of your system. So the energy of the system is a function, is a functional, because it's a function of the density, the three-dimensional variable. What this means is that the Schrödinger equation now is much easier to solve. Instead of solving for the wave function that has many variables, 3 degrees of freedom per atom plus spin if you have it, now you have one variable that has 3 degrees of freedom in total. Not 3n, but 3. Because the electron density is a three-dimensional function. So it's a functional of it has 3 parts. One of the kinetic energy, which is a functional of the density. One of the electron-electron interaction, which is a functional of the density. And these are always the same for any material. And then one part that depends on the external potential. The problem is it's not known what this functional is. So it's proved that it exists. It's not known which one it is. So the following year, Kohn and Sham made an approximation that makes this treatable, which is to consider the electron density as made from non-interacting electrons. Again, I said before, if the electrons didn't interact, then it would be possible to solve this. It's a very the wave you can get it with orbitals that are uncoupled. So for each electron, you get like in any simple quantum mechanics problem, you get a wave function and you fill levels as you go. But they are coupled, so you cannot do this. But you can still think of what if the density of electrons I have was the one of a system of electrons that does not interact. And then what you would have is a different potential. This is not created by that potential. It's created by a different potential that is the Kohn-Sham potential. So with the Kohn-Sham potential, then you solve for these easier orbitals. Now it's not the whole wave function of the system, but it's one orbital per electron. You take the lowest occupied orbitals, you fill them according to the Fermi principle, exclusion principle, and you get the density, okay? Which is the same. Now, the thing is, you have to deal with this, and the way to do it is going back to orbitals, so it doesn't, I'm not going to give more details, I want just to give you the idea, that you basically rearrange the terms so that you have the kinetic energy, but now of the non-interacting electrons, the Hartree potential, which is the simplest way in which electrons interact among each other, so you just integrate for all possible interaction between electrons, and the external potential and something else, which we don't know, which is what goes from here to here and from here to here. Because again, as we said, we are talking now about an artificial system. So this is not this, and this is not this. There is a difference which goes here. This difference is small. It's a small term. And there are many approximations for it, but they are approximations. So when if you read papers about DFT and you see local density approximation or generalized gradient approximations, they are clever ways to come with this term. Okay? This is not exact, it's approximate, and you have to know when they work and when they don't. So how do you, so now you have the basic theory, which was done in the 60s. How do you apply this? Well, you usually use a code that someone has done. This is not like the case of the hard spheres that you can code it in a few hours. These codes take usually a group of people to code for a few years, and for many times these codes were property of the research group, like in the at the end of the 70s, 80s. Each group had their code that they coded for many years. Many people was their tool. They didn't let it to anyone to use it. In the 90s, this changed with the, I guess, with the Linux system and this other kind of approach to production of software. Many of these codes were made available. So codes like BIMnO and Quantum Espresso are very good codes that have a lot of effort made of them, and they are free. You can not only you don't pay, you can download them, you can change them, call them whatever, My Quantum Espresso, and start a new branch if you want. They are free software in the real meaning of free software. There are other codes that you don't pay, but they are not free, so they don't allow you to make changes, like Siesta. They use plane waves, and this is a kind of a big difference between one kind of code and the other kind of code. There are two big groups. There are more, but there are two big ones. You use plane waves as you are always going to solve differential equations that are like Schrödinger's equation, and you always are going to need a basis set to expand your wave functions. This could be plane waves. Plane waves are just what you know, sines and cosines. Or you could use something that looks like the orbitals of hydrogen, for example. So localized basis set. The advantage of plane waves is that they are very democratic. They are not affected by what atom you have there, where is the atom, is my basis set localized on the atom or not, because they go to infinity. It doesn't matter where you put them. I mean, actually, you don't put them anywhere. They are in all your simulation box. What is the disadvantage? They are slower, because you have many, and precisely because you have not told the system that you already know that electrons are not in a solid, they are not everywhere in general. They look more like orbitals in a hydrogen atom, or they look in general in between an orbital in a hydrogen atom and something else like a plane wave. So, but these are very robust and very easy to use because of that. If your basis set is not complete, so I mean your basis set is never complete, but if your accuracy of the calculation that depends on the basis set is not good enough, you put more, and that's it. You pay more price, but you put more plane waves, and at some point the result will not change. It's more difficult to do that with orbitals because it depends on what orbital you put. If your material, for some reason, the f orbitals are important, it doesn't matter if you put 20 d orbitals, you might not get the effect you want. So you need to know more in this kind of code than in that one. VASP is like these two, so plane waves. So these three should give you the same answer. If you go there, you want to know what is the bond distance in diamond from first principles. These three should give you the same answer. VASP is not free. You have to pay 4,000 euros for it, but it the difference between them is that they implement different functionalities. Every year, a new method to do something comes out, a new exchange correlation functional, a new way to treat optics, a new way to do something. VASP has a lot of this. Others, they don't have it yet, they will have it eventually, so it all depends again on what kind of system you need to work with. In our group, we have worked a bit with Siesta. The other thing that makes Siesta particular, we have worked a bit in the development, in adding routines to Siesta, not in the core development, but in one of these extra things that codes do. What makes Siesta particular is that while the plane waves codes, if you double your number of atoms, you will have to make computations for 4 to 8 times more time. So the scaling is in principle with the cube of the number of atoms, but because there are different terms and they not all scale equally, it's not true that it's exactly the cube, but it will be close to that. Siesta was built because it uses localized atoms. Then if my system is big, but an atom here will not see anything related to an atom here. In a plane wave, yes, because there will be a plane wave all across the system. In Siesta, not. So all the algorithms have been designed to be linear scaling, which means that if you double the number of atoms, you only pay twice the number of time. So if your system is small, Siesta will do worse in computer time. If your system is big, Siesta will do better. And if everything is well done, you will again get the same answer as in the plane wave codes. So what do we do and what can we expect from the density functional theory? Now we have a tool to learn about materials. What can we learn and how careful do we have to be? So if you want to learn about the geometry of your material, if you have a crystal that is new because you are substituting, you are taking the crystal every experimentalist is growing, and you want to know what happens if you put lanthanum instead of gadolinium, you will get the bond length, if you do things properly, within an error of 1% of that experiment that they will do later and show how good your calculation is. Or more typically, if you want to reproduce an experimental result, you can build the crystal, run it, and see what is the distance between bonds, and you should get around 1% of error with the experiment. And moreover, this error should be systematic. So if you are using local density approximation, it should be always, your bonds are always shorter. If you are using GGA, your bonds are always larger. If you get something that is not like this, either you made a mistake or you pick the wrong method. There is something in your system that you should have known. Your system has whatever localized electrons that you have to be careful about. You should have known, and you should have get the right answer. So you always have to make sure the numbers you get fit some physical intuition. If you want to compare several phases of a crystal, you will get, and to know which one is the ground state, you will basically always get correctly the ground state. Again, if you don't, there is something else you have to learn. Something is not taken properly into account. It's not just that the method sometimes fails. Well, it fails for a reason always. If you want to compute formation energies, then you will get an error that is substantial, but in many cases it's also systematic, 10 to 20%. In our group, we are interested in magnetic materials and in ferroelectric materials, usually insulators, so I know much less about metals. Magnetic orderings will come correctly most of the time in my experience, and magnetic moments too. If you have things like orbital ordering, it will come correctly too, if you do things properly. And things like electric polarization that we always compute, because we many times do ferroelectrics, will be again 10, 20% accurate. So for these things, if you know your kind of materials, you can be quite confident. But you have to always be careful. And typical examples where you have to be careful is if your material has van der Waals interactions. If you are interested in organic molecules deposited in a metal film, then you have to be careful. Even things as simple as if you are interested in graphite, you will get an error in the distance between the layers that might be 20%. I was once doing calculations for sulfur, and sulfur has a very interesting unit cell with 128 atoms in crowns of rings of 8 atoms, and every ring and every other ring interact with van der Waals forces. Okay? You get an error in the lattice parameter of 20%. This is not just, well, for sulfur, DFT does 20%. You have to understand that you have a van der Waals system and you have to do something about it. Now there are recipes to cure this. There are many different methods implemented that, again, based on physics, will correct for this. Another typical thing that happens, for example, in our oxides, is that if you have D or F electrons, these electrons are very much localized. In this case, DFT, which is a theory that DFT with local density approximation will fail most of the time. You need to correct for this. You have to over-localize what DFT gives you. And there are ways for doing this systematically, and are known to work for this kind of material. And the other thing that is very typical and is very well known is that typical DFT will give you wrong band gaps. You can get a band gap that is half the band gap of the material. Actually, you will never, with LDA, basically only by accident you can get a right band gap. But again, if you are willing to pay the price of computer time, there are ways to cure this. And if you really need to know the band gap very accurately, methods like which include correlation, like GW, are very expensive computationally, but you can see how well they do. This is the theoretical band gap, and this is the experimental band gap for these materials. And the triangles are GW. You get it very well, at least for these materials and related materials. Sorry. So I wanted now to mention one study we do, so I can tell you a bit more of what you would expect to do if you were to do first principles calculations. In this case, we are interested in ferroelectrics that can be grown as epitaxial films on top of a substrate. Okay? We know that the strain that if you grow this with molecular beam epitaxy, you begin to grow layers little by little, and the atoms will fit the positions that this material allows them to fit. So instead of growing like a single crystal of barium titanate, they will grow like a crystal of barium titanate that was somehow constrained. It has a stress in 2 dimensions. We want to know how this strain affects materials. This has been a line of the work I've been doing for several years now. So we use a strain to control these things. Again, just this transparency, just to explain what a ferroelectric is, or just to mention what a ferroelectric is. Usually you are used to ferromagnets. Ferromagnets are materials usually used, for example, for storing information, for memories. You apply a magnetic field, and the magnetization of the material saturates at one point here. If you remove the magnetic field, the material is ferroelectric, so it will keep a magnetization. If you apply a magnetic field in the other way, it will change orientation, the magnetization. And this is how you store memory. Okay? You have 2 possible orientations of the magnetization, and you switch between them. It's possible to do the same with with some polar materials. If you can do it, then you have a ferroelectric. So again, now what you have is a displacement of charge. The center of mass of the positive charge in your solid does not coincide with the center of mass of the negative charge. There is no center of symmetry. If you can, so the solid has a polarization. If you can switch it, you have a ferroelectric. In a few materials are multiferroic, which means show both behaviors, but for this talk, it doesn't really matter. there was one material called bismuth ferrite, which is the prototype of multiferroics, but has some problems. Again, it doesn't really matter. So what matters is we want to find a material that is a better multiferroic than the one known. So one way to start searching is in the family of this material. So that is bismuth ferrite. So an oxide with a transition metal that is iron. We can look at the cousins of iron. So there is the bismuth scandiate, bismuth chromate, bismuth manganite, our bismuth ferrite, etc. All these, the ones that are not here, don't exist as perovskites, but these ones do in bulk form. We want to but only this one is ferromagnet. Actually, bismuth manganite is the only insulator that is a robust ferromagnet. So we want to know more about it. Why is not used instead of bismuth ferrite, if bismuth ferrite has some problems? Well, it's not used because it's a ferromagnet, but it's not ferroelectric. It has what I told you about the center of mass of the charges. In this case, one is on top of the other. It's a center-symmetric structure. It's a very odd one because it has orbital ordering. This means that there is a occupied dz2 electron that whose orbital, there is an electron that occupies a dz2 orbital that is oriented in different directions. Half of the manganese is oriented in this way and half is in that way. So the distance between manganese and oxygen in this way is much larger than in this way. In this way is 2.2 angstroms, in the other way is 1.9. This particular geometry is what makes bismuth, this particular geometry, and that the bismuth is manganese plus 3 is a D4 ion, is what makes, which has 4 electrons with the same spin, is what makes this ferromagnetic. So, but it's not ferroelectric. Can we make it both? This was the idea of the study. So for this, we did what I think are typical DFT calculations that you would expect to do if you begin to work in this field. We have a set of suspects that we think can be stable phases of this material or metastable. It doesn't matter now how we rounded up these suspects. We have them. So we can run density functional theory calculations for them and see who is expected to be the ground state. And we better get the ground state as the experimental ground state. If not, something is wrong. So we know that manganese is a tough ion is a d electron ion with localized orbitals, so we don't use DFT, we use a correction to it. We put a penalty so that those electrons come localized, and usually this works, and this works for bismuth ferrite and for many other materials. But it doesn't work for bismuth manganite. We tried different ways to penalize this material, and it never happened. First, we never got the ferromagnetic state because it closes the gap. It's a metal, but we know that experimentally it's an insulator. So something is wrong. And there is a phase that is more stable than the ground state. So we looked at the band structure of the material and we realized it's impossible to open the band gap within DFT. So we resorted to something that is 100 times more expensive, but that is known to work for these oxides, which is a hybrid method. It doesn't really matter what we do. We mix density functional theory with another method that does better at compute. It doesn't really matter what we do. If you are interested, I can tell you. So what now? Now we have something that seems to work. We found some bulk structures that are metastable, in the same way that diamond is metastable with respect to graphite. So now we want diamond. We don't want graphite. How do we get it? One way is growing these materials as films, as I said. So what we did is one calculation for every possible distance that the substrate can have between their atoms, and we checked what is the energy. We check it for the ground state, and we check it for two particularly low phases that we want to stabilize. And indeed, if you go far enough from the ground state lattice constant, this phase is more stable than this phase is more stable than this phase, and these phases are ferroelectric. Now, there are reasons. Again, this in principle doesn't mean anything. This could be totally unrealistic energy, or this could be a totally unrealistic strain. And these things are very important, and you have to check if this is true or it's not true. You have to address it, because it's a criticism you'll get. It doesn't matter why. I can tell you that it makes sense, and we think if you grow bismuth manganite on this kind of substrate, yttrium aluminate that has that lattice constant, you will get a ferroelectric. Now, how did we do the calculations? We did them with VASP, and I just want to show a bit more detail of things you never see in a talk. You need to give VASP a list of parameters that take care of the numerical accuracy. There is no other thing here. These parameters just take care of how well converged your results are going to be. Includes the things like how many plane waves you want. It doesn't really matter what. The important thing is, if the values are correct, you will get a good result, I mean, as within DFT. But you can turn all these knobs to the best performance possible, but then your calculation will never finish. Okay? So always when you do calculations, you have to do tests to see when you get accurate results, but without spending too much time. So this is one of the 4 files you need. You need another file in which, again, you converge calculations. This is something called K points. You need to do integrations in reciprocal space of usually smooth functions. So you just need a few integration grid points. It doesn't really matter for now. It matters a lot because every point you put, extra point, you pay a lot of computer time. And you have to give the coordinates, the guess coordinates. You have to guess some coordinates for your crystal. You give the lattice vectors and the coordinates. And this is what you need. Then you need a file that contains what is called a pseudopotential, or or a refinement of a pseudopotential. This usually you don't generate yourself, although it's very good if you do. This, again, usually also goes not much talk about it. This, what it does is, by using pseudopotentials, you are not taking into account the core electrons in your atoms, other than by assuming that the other electrons, the valence electrons, the ones that are going to give you chemical bonding, will fill them just as a potential, basically. Then there are many elaborations on this, but this is the idea. And you will always have to get these files from somewhere. Either you generate them yourself with another program, or you go to a paper where they did the calculation for your system. You see that they use some pseudopotential that is available on the internet, and you download it because they already tested. You should also test it anyway. So I'm running out of time, but I guess this will be the last point I make. And again, I also said this yesterday. So now we have this bismuth manganite that is a ferroelectric, as we wanted, but is not a ferromagnet anymore. If I look at we can compute, again, the difference between magnetic orderings and this kind of magnetic ordering, where in the layers parallel to the plane, all the spins of manganese pointing one way, and in the next layer in the opposite way, is more stable than the ferromagnetic I wanted. It's not by much, and these differences, for example, are much smaller than in bismuth ferrite, but it comes out more stable. Now, we could go on about it, things you can do to try to make it ferromagnetic by mixing impurities, etc., by thinking of what gives you ferromagnetic interactions or antiferromagnetic. We could do that, but the point of this transparency is everything I've done so far is for 0 temperature of these materials. So for my oxides, the melting temperature of this is around 1000 K for things like bismuth ferrite, and there is no phase transition. So I'm not that much worried that that entropic effects will make my phases change how likely they are to appear. But I would like to know when the magnetic transition occurs. I would like to know when, well, as you probably know, if you have a ferromagnet or antiferromagnet and you raise the temperature, there is a transition to a point in which the material loses the magnetic moment. The spins point in random directions. I want to know for which temperature. But at DFT, I can only do calculations at 0 temperature. Doing calculations at finite temperature, there are several ways to go about it. One of the ways to go about it, a simple one, is just to take into account that there will be a Boltzmann distribution of the energy configurations, and to compute the average energy, take into account this Boltzmann factor. If you do this, you need to do whatever, 100,000 evaluations of energies for different phases, for different positions of your atoms. It's impossible you are going to do that with DFT, because it took, every point you see there, maybe took 3 days. If I need to do 100,000 of those, I will never finish. So this is why I always, why I said before, this is an illustration that you have to pick the right method. So one way to go about it is to use the DFT to feed some other method that is simpler, but that is able to reproduce the results. So what we do is we assume that the differences in energy, because these spins change, follow a Heisenberg model in which the differences in energy just depend on how many pairs you have oriented in how many ways. And moreover, we cut the model at first neighbors. So we only take JC and JA. So for every iron, we look at the 6 closest neighbors, and we fit a Hamiltonian. So now, instead of doing 3 days of calculations, I can do 0.1 second of calculation and get the energy. So I can do many of them. So I can find out that the transition temperature is around 100 K, so quite low. And I have reasons to believe that this is accurate, because we've done it for materials where we know the experimental one. And with this, I'm going to finish. If you are interested in learning a bit more about it, there are 2 good references. This is a classic one. It's a review with many pages about ab initio calculations in the 90s, at the point of the transition between when the codes were made available. This is a very introduction I like to density functional theory. And then Wikipedia is quite good I've checked some of the electronic structure pages, and it's good to get you started and to give you references. And many of the codes I said, Abinit, Quantum Espresso, Siesta, they have tutorials, manuals, video talks in their web pages. All this is free. With this little ad, I'll finish.
Talk. As Oswaldo just shows the ad, but I will add on top of it. So Oswaldo is going to be for the first time at Tel Aviv University, and next in the coming semester a course on atomistic simulation of materials. We have compulsory courses. We also have a compulsory course for undergraduate students, which is not even this year. And for those of you who are interested, you are more than welcome to approach him with respect to potential MSc or PhD thesis under his advisory. Any questions? Shahar.
I was wondering, I mean, your input includes the atomic coordinates. So how do you know at the end of your simulations that your results does not sit at, for example, a local minima?
That's a good question. You don't know. You never know. until you run several. I mean, if you want to do it well, you can start by symmetry considerations. So if you give the program some symmetry group, it will stay in it, or it will go to a higher one, never to a lower one. What I usually do is I give initial coordinates with random noise, so that I have no symmetry imposed, and I do it several times. And if I see that all the time they go to the same minimum, I'm happy with it.
David.
There was a Northwestern connection to molecular dynamics. The son of Bernie Orza is a professor of history, mainly history of science at Northwestern. Quite a good one.
Okay.
The other question I had, which is also historical. You know, there was, on the east coast of the United States, Vineyard at Brookhaven and Milgram at New York University, and some other people wrote an MD code to study radiation damage. And I'm not sure who came out first, but that MD code had a tremendous influence on the field of radiation damage. I'm sure you know all.
I mean, I say yes because I know people that study radiation damage. It's a difficult problem because the Born-Oppenheimer approximation I mentioned as something guaranteed not necessarily works anymore. But I know of people. I know that there is a classic paper of this that maybe is this group.
It's Vineyard, Milgram.
Yeah, I forgot the. I thought of using that paper in my course to try to reproduce it.
Cover of Journal of Applied Physics.
But how recent is this? When did they?
At about the same time as all this paper. But
Okay, so yes, it's the same.
What happened with time is that as the computers became more powerful, then the knock-on energy became very high, and people could actually see displacement cascades, for fairly energetic ones.
I'm aware that they do this, and that is not a standard, but that is possible to do it.
So how well do you do with TC barium titanate?
Not that well. There are several things there. There is, I mean, the simulations I'm aware of, they were done with local density approximation, and there is an inherent error there, but maybe it's not that big. Also, they didn't take into account an harmonic effects, and again, this might be, say, 50% one of the errors, 50% of the other. They did show that the 0-point motion corrections were important. There is in this particular field, the group of David Vanderbilt has done research, and there is a paper in which they get quite accurate, not quite accurate, but much better results than usual by taking into account the 0-point motion. So short answer would be, if you use typical DFT, you get an error of 100 degrees in the transitions. If you correct for quantum point motion, you reduce this error to, I don't remember, but maybe half. If you could correct for local density approximation and harmonicities, would be nice to see it. Maybe it will correct everything.
So do you do all these corrections in your work or not?
Myself?
Yeah,
No, but I'm not. But I'm not measuring ferroelectric transition temperature.
What else is there? I mean, is the transition temperature and the interaction energy?
But for the materials I'm interested in, I'm talking about materials whose Curie temperature is 1,000 Kelvin. I'm not going there. I'm trying to find other materials that have whatever effect I'm looking for, but at room temperature. Once I find that bismuth manganite is ferroelectric at room temperature, I cannot tell you if it will transition to paraelectric at 900 or 1,000. But okay, I would like to do it, but it's not what I'm.
So you use robust ferroelectrics, but weak ferromagnets.
Well, the ferromagnets are usually weak, in temperature, so yes. When I compare ferromagnetic transition temperatures to experiment, they come very well for the ones I've done, for my family of experiments.
Then I need quantum mechanics calculation. So you need a pseudo potential for the code to work.
Yes.
Is the potential a function of the material? In other
It's-
words, whether it's an oxide?
It's a function only of the atom you have. So, but there is a lot to say about it. Maybe not. So,
Maybe the coffee.
Okay.
Any more questions before the coffee break? So if not, let's thank